a test on Tuesday, right? That's what we agreed on. So exam 1 is Tuesday. That would be the 7th.
Is this like a speak now or forever hold your peace thing? Can we disagree?
I mean, I guess I could go back to the video and find out. I was just hoping you would give me total support on that, you know?
Okay.
Or like, I thought maybe there was a chance I would say like, yeah, did we agree on that? And you'd be like, who are you? This isn't even a real class. We're just sitting in here. Okay, so the topics are everything up through rigid body, free body diagrams. So there's no rigid body statics, and so all of the stuff that we talked about, at least most of the time last class, and all of today, it's not going to be on the test. And where we ended last class was just going through the list of joints in 3D. Before I go back to that, does anyone have any homework questions or general questions related to the test? Yep.
Can I draw it for you real quick?
Yeah.
Actually, yeah, I'll just draw.
I'll do yours next, okay?
I was just going to ask, how many questions?
Oh, I always try to make these exams, these 80-minute exams. So like when I'm writing it, I'm thinking half the class I want to have left after 1 hour. So how many questions? It just depends on what the topic is. Later on, there'll be tests that are just basically one question. So if it's a lot of vector questions, then there'll be more because those are quicker. If it's, if it's complicated particle statics problems, there might just be 2. Probably 3 is the average, I would guess, 3 or 4. Okay.
So this joint, this contact point right here.
Yeah.
There's no moment about that point, correct?
Right.
Because it'll do it. And why not? What exactly do you need for there to be a moment?
Okay, so let me draw it.
I understand that. I understand that. This part in the separate question does have a moment about that point.
Okay, so this is rigid body problems. Okay, so this is about the rigid body. Is it just a free body diagram? Okay. And there's a cable connected that goes over a pulley. And there's a mass hanging. This is 10 kilograms. This is 75 kilograms. Okay, and you have to draw a free body diagram of that. So how do you treat this joint, or how do you know how to treat the contact between the left end and the wall? Well, in order for this to be solvable, this is a rigid body problem, a single rigid body, a 2D problem. So how many equations are you going to get out of this? Did someone say 2 and someone say 4? You're going to get 3. So your average answer is just right. You're going to get 2 from Newton's second law and 1 from the rotational equation. So think about how many variables are you going to get at this pin and slot joint? What do you know about that joint? rotate. Yep. Yeah, let's think about it that way. It can rotate freely, so we know there's no couple. And it can slide freely along the slot, so we know there's no force there. And so 2 degrees of freedom remain. There's going to be one variable. So that means that for this to be solvable, or for this system to stay static, we need this to give us 2 variables. Otherwise, we'd have 3 equations, 2 variables. And I mean, there are some cases where it would work out, but generally, you need 1 variable for every equation you have, or your system's overdetermined. So anyways, that's a long way of saying, if the problem didn't tell you what kind of joint this was, you know you probably want to treat it as a friction contact because you need 2 variables from this joint. And you can, just intuitively, you can imagine if this was frictionless, this thing could slide that way, that would slide up, you know. So anyways, the idea is that that's a friction contact. And a friction contact you treat as a fully unknown force vector. You have that tension here, which would end up being 98.1. You have the weight here, 75 times 9.81 is, I feel like I know that one, 735. 735.75. And then this, if the slot is this way, the force is perpendicular to that. I don't know, I'll call that F. Some of the joints that give you a known direction force vector have, you know, the value is required to be positive. What about this one? What if you went through the calculations and you got a negative answer for that F? That's right. And this kind of joint can apply forces in either direction. If you try to push that pin this way, the slot will push back that way. If you try to pull the pin that way, the slot will pull back that way. So this can be positive or negative. Any other homework questions? Yep. About this one? Yeah. No, perpendicular. It's supposed to be perpendicular to the slot. Because yep. Of the beam? Yes. All right. Well, the only, think about it like this. This is free to move this way, right? Yeah. So it can't provide any component of force parallel to that slot. And so the only way it can apply a force is perpendicular to that slot. Anything that's not perpendicular to the slot would have some component that's parallel. And we know that that slot can't provide a component parallel. If you have a force that's parallel to the beam this way or that way, yeah, all that does is put the beam in pure tension or pure compression. And you can imagine with this setup, if you applied a big force down on the middle here, this could provide enough force that this thing would start to bend, you know. So this is capable of applying forces that don't just put it into pure tension or compression. Okay. There is one thing that maybe this is what you're thinking about. If you have, and I'll talk about this more later, but if you have any member that only has two force vectors applied to it, then those forces, those two force vectors have to be equal and opposite, and they both have to be parallel to the, actually it's to the line between where the forces are applied. So in that case, you know, if the only forces on this were a force here and a force here, those forces would have to be parallel to the beam. But this one has a bunch of forces acting. Well, you know, 1, 2, 3, 4 different forces. So you can't use the assumption of two forces.
On the first rigid body statics problem,
Mhm.
in your solution, you've got, like in the force table, in addition to the rho and force MA, you've got a P
Oh.
and an A vector. I've never seen
Okay, right. That's the way I used to talk about it. I thought I'd gotten all those out of the solutions, but I better look back at them. So just scribble that out, and then it's, you know, just ignore the P and the A. Okay, but what that is P is the coordinates of where the force is applied, and A is the coordinates of the about point. And then if you do it that way, you can just subtract those two, and it gives you the rho vector. But I think it's simpler and a better way to think about it to just go straight to the rho vector.
Would be just cross that.
Yeah, right. Then it's exactly what we're doing in class.
first.
So whenever you're doing rigid body statics problems,
Mhm.
you do the summation of the forces, do the second law,
Mhm.
and then you also do another thing for the moments.
Yes.
And then whenever you're putting those in, you put those in a matrix? Or do you solve them all?
You're just solving a system of equations, and you can do that however you want. But when you're doing three-dimensional problems, you probably want to put it in a matrix, because otherwise it's sort of tedious to solve, you know, 6 equations by substitution or something. But you're welcome to solve it however you want. We are later, when we get into structures where we have a bunch of rigid bodies connected by joints, we're going to end up with systems of 15 or 20 equations, and then you pretty much, you have to do it by a matrix. I mean, if you try to do that by substitution, it would take forever. Okay. Any other questions? Okay. So let's go back to 3D joints.
So if we know how to do it in practice,
Mhm.
we should know how to do it.
Yeah, here's how I would think about it. If you, so what you don't want to do is like just memorize those problems, because it's not going to be those problems on the test. But if you can get to the point where on any one of those problems, you could explain to somebody why you made each choice at each step, you can understand them to that level, then yeah, the test will go fine. Great. Okay. Okay, so we were done with joint category 4. We were done with the type of joint that adds 4 variables to Newton's laws. Now we're going on to joint category 5. This joint category thing, that's not like a technical term or anything. That's just how I'm describing it. You know what I mean? That's not like, don't go to your boss and talk about joint category 5 or whatever. It doesn't mean anything. Okay, so joint category 5. This is a joint that introduces up to 5 variables. And it does it by introducing 3 force components and 2 couple components And just like with the last one, remember we had these couples that were only added if they were needed for equilibrium, and it's the same thing here. So these two couple components are only going to be used if they're needed for equilibrium. And this is, so the last one, the one that introduced 4 variables, was a pin joint that didn't provide any thrust. That was a pin joint that the two objects could slide relative to each other along the pin. So now we just have a pin joint, same idea, but now there is thrust, so they're fixed along that axis. Okay, they can't slide relative to each other. So pin with thrust.
Just like the one above, except with maybe dots on the outside of those.
Yes, exactly. Yep. I'm going to draw it as like brackets, but yeah, that's exactly the right idea.
This is just basically like a hinge.
Right. Yep. And let me show a demo of that. I've already showed you this one. But this is a pin joint that provides thrust. You can see that that pin has, like the pin that goes through here is thin, but it has little flanges on the outside, so the pin can't slide, and these two things are locked in place by that bracket. So let's think about what degrees of freedom are limited. So it's free to rotate this way. So we know there's one component of a couple at least that that isn't applied. Okay, there's no couple applied about that axis, but I can't twist it like this, and I can't twist it like, let's see, I can't lift this up and down. So that's two components of a couple that it applies. And then I can't translate it in any direction. I can't pull this that way. I can't push it up and down. And now what's new with this one is I also can't get these to translate along the axis. Okay, so that's the 5 loads that are applied. So I'm going to use a coordinate system with the z-axis this way.
Still on the camera.
Nope. Thanks. Okay, so coordinate system with the z-axis this way, the x-axis this way, y-axis up. And a free body diagram of that beam. We know that there are 3 components of force. So we know there's a force vector, I'll call it R. Make a little space here. And now for the couples, there's a couple about the x-axis, a couple about the y-axis, and no couple about the z-axis because that's where it's free to rotate. So I'm going to draw a couple component like that, one like that, And I'll call this mx and my. And mx and my are are only there if they're needed for equilibrium. Okay, so another way to think of that is every degree of freedom is limited except rotation about the axis. Okay. And then the last category, joint category 6. Yeah. I'll go into that a little more, but if you could do the statics problem without those moments there, and you could solve for the values without those couples included, then leave them out. That's what I mean. Like if you have, if those couples bring too many variables into the equation to solve it, then leave them out. I'll do some examples though. So joint category 6. Well, there's 6 degrees of freedom. This is the joint that introduces 6 variables. And so what kind of motion is allowed by this joint? None, right? It's just fixed. And it's usually just drawn like that, like the member just runs into a wall or something and just terminates there. Free body diagram looks like this. You have a full force vector and a full couple vector, so I'll draw all these components.
Can you draw couples like that, or like
In 3D, do it like that because it'll get really messy trying to make it clear what axis you're rotating about. You know what I mean? Like you would have to, in 3D, you'd have to do it like this. And it's just tedious and really easy to be confusing. So this works better in 3D, but in 2D, yeah, you could do either one. Okay, so let me go back to what I was saying about whether you need those couples or not. So in the pin joints, when do you and don't you need to use those couples for equilibrium? There's really one example that is going to be virtually all the times that you don't use those couples. There are probably other examples, but this is a really good example of, I think, when you don't need to use those couples. So don't use those couples. And there are 2 points. Along the same axis. So that would look something like this. Okay, so I have something sort of like this. Let me try to show it to you. Okay, so go back to this one first. In this case, say that I try to cause a rotation that's about something besides this main axis. Okay, so say that I try to twist these 2 pieces. Okay, what prevents me from doing that? Like physically, what's preventing me from twisting my hands? Yeah, that bracket there, and yeah, right. So the joint itself is applying a couple that's along the axis, that like my hands are holding, that's keeping me from doing this rotation, right? So now let's look at this one, and I'm going to try to do the same thing. Okay, so here's 2 pin joints that share an axis, and I'm going to try to twist this piece with my left hand. In that case, is it the couple that's provided by the brackets that's mainly keeping me from being able to twist that? Or is it just the fact that, like, notice that if I try to twist it this way, okay, that's trying to make this side come out and this side go in, okay? And that can be prevented without any couples at this joint or this joint, just by this pushing down and this pulling up, okay? So in this case, I'm prevented from twisting this, torquing this thing, by forces at the 2 pin joints, not by couples at the 2 pin joints, okay? So in this case, where there are 2 pin joints that share an axis of rotation, this thing, the degrees of freedom that are limited here can all be done without those couples being present. Okay, so if you have a case like that, where you have 2 pin joints that share an axis, you always just represent these joints in terms of forces. I did it again.
So based on that, couldn't most couples just be described as, instead of rotational, just 2 linear forces acting? Some level.
Yes, well, that's what a couple is 2 different forces acting. So yes, but the difference is that in this case, like if you just have 1 pin joint, that couple is applied by 2 forces very close to each other inside the joint itself that's causing that moment. In this case, 1 force is applied by this pin and the other force is applied by this pin. Okay. So the free body diagram in this case And assuming that this is, these are pin joints that don't provide any thrust, would just be a force vector here and a force vector here.
So without thrust, that means it's free to slide.
That's right. So let me do draw a picture of one where one of these pin joints does apply thrust.
Would that mean that there's, in your free body diagram, should there be horizontal?
Oh yeah, right. Yes, very good. So this shouldn't have that component. And then, so if I draw one that does have thrust, that's right. Yep. Okay, so let's say now we have something like this. Okay, so this time that bracket is surrounded by two of these flanges that keep the pin from sliding through on the left side. Okay. So then in that case, so this provides thrust. The free body diagram looks like this. Over here, we have a full force vector. And over here, since there's no thrust provided on the right side, we just have that and that. Any questions about that? Yeah.
So in this case, are we going to be using those torque?
No, in these you don't. But you would if you had a problem where there was just a single pin joint. Okay. Because a single pin joint, it will resist rotation on its own. It won't do it with a couple in the joint itself if there's another way to prevent that rotation. And so in problems like this, where you have two pin joints that share an axis, all the rotations that are prevented can be prevented just by these forces. So that's all you use. Any other questions about that? Yeah. Okay, yeah, because the idea was, let me show another one of these. Okay, so this is the one I showed you before. There's no thrust there. That's free to, so there's no thrust at either one of these pins. At both pins, it allows this axis to slide like that. One that has thrust on one side. It's a little hard to see. But on this side, there's little flanges on the axis that keep it from sliding through the pin joint. Okay, so In this case, this is still the same as it was in the other one. If it was up to this one, that axis would still be able to slide. But there's thrust provided at the other one by that flange. And so that's what's going on in this. This is supposed to be a flange that keeps the axis from sliding through on the left side. There's nothing like that on the right side. So there's a force along the axis provided by the flange on this one side and nothing provided on the other side. So that's thrust. That's whether the joint has thrust or not.
So that there would actually be no component in along the axis if there was no outside force actually making the thrust work, right?
That's true. Yep,
Otherwise it would just
that's right. But that's something you could solve for, so you don't have to think about that ahead of time. When you do problems like this, you just go through the rules of the joints, write down whatever loads are applied by that joint, and then when you put them in the equations, if some end up being zero, you can solve for that. Okay. Any other questions? Okay, let me do a couple example problems. So the first one is there's a big rectangular sign. And it's connected to the wall by a ball and socket joint. So here's the ball and socket joint. And it's supported by two cables. One that goes from this point C to a spot above it on the wall. And another one that goes from the end of the sign at D to above it on the other side of the wall. Okay, can you follow what that's supposed to look like? And this distance is 2 meters. And this distance is 0.5 meters. The height of the sign is 1.5 meters. And then the distances for these connections, this length is 1 meter. This height is 1 meter. The horizontal distance on the other side is 2 meters. And the vertical distance on the other side is 1.5 meters. And the mass of this sign is 50 kilograms. Yes, that's right. Yep. Well, D, no, not D. Yeah, right. That's each of these two is above that the ball and socket joint. Each of these 2 points is the same height as the ball and socket. And we want to know what are the cable tensions. Well, what are the cable tensions and what's the force vector applied by the ball and socket joint? And I'm going to give you a coordinate system. Let's say the x-axis goes out along the sine. Y-axis is up. And the z-axis then has to be this way. Okay, so the first step is a free body diagram. So there's the body. At the middle, a weight force is applied, so that's 50 times 9.81, 490.5. What kind of loads are applied by a ball and socket joint? Yep, just a force vector. So let's see. Yeah, I forgot to name all these joints. That'll make it easier to follow this. So there's C and D. The joint, well, I guess I didn't name that one. The connection on the left to the wall is A, and the other connection is B. Okay, so we'll call that force vector R. And then where else are there forces applied to the boundary by the outside world? 2 cable tensions. So there's one over here that I'll call TA, the cable tension going to the point A, and then another one at the end that I'll call TB. Anything else? That should be it. Okay, so let's count up the variables now and think about if it is possible that this will work. We have 3 variables in R, 1 at each of these. So right now we have 5 variables. We know that we're going to get 6 equations from Newton's laws. So that's something to sort of keep your eye on. What we need is for one of those equations from Newton's laws to end up being either a linear combination of other equations or to be like a degenerate equation like 0 equals 0. Okay? If one of our equations doesn't go away, then we can't solve this. Okay? Because we can only solve a system of 5 equations for 5 variables. Okay, so then rho vector, force vector, moment. And we have to choose an about point. Like usual, best approach is to choose your about point where you have the most unknown forces. So I'm going to put it right here at the ball and socket joint. Okay, so for the force R, what's the rho vector? 0. The force vector is Rx, Ry, Rz, and the cross product is 0. Next is the weight force. So what's the vector to get from the origin to the center of that rectangle? How far do we have to go in the x direction? Exactly. The whole thing is 2.5 meters long. So to get to the middle is 1.25 meters. In the positive x direction. And how far do we have to go in the y direction? Half of the height, and in the negative direction. And how far in the z direction? 0. Yep. And then the force is 490.5 in the negative y direction. So 0, negative 490.5, 0. And that cross product is 0, 0, negative 613.13. And now the two cable forces. So first let's do this cable force TA. How far in the x direction do you have to go from the ball and socket joint to that point C? 2 meters. How far in the y direction? 0. How far in the z direction? 0. And now we have to figure out what that force vector is. We haven't done that yet. How are we going to do that? What's going to be the approach for coming up with the force vector applied by that cable? You know, in 3D, you probably don't ever want to try to find the angle. You could, but it's just tedious. What works way better in 3D is represent that point with coordinates, represent that point with coordinates, and then just subtract. So you get a vector that's pointing in that direction, and then just take a unit vector, you know, divided by its length to get a unit vector in that direction. Okay, so we can think of what the coordinates of A are, what the coordinates of C are, and then a vector going in the direction of this force TA is A minus C. So the coordinates of A in this coordinate system, what is that? Yeah. So 0, 1, 1. And the coordinates of C is, I guess that's what we just did here. That's 2, 0, 0. So a vector in the right direction, I'll call it U, is A minus C. So that's negative 2, 1, 1. The length of that vector is 2 squared plus 1 squared plus 1 squared square root. So square root of 6. And so the unit vector is negative 2 over the square root of 6, positive 1 over the square root of 6, positive 1 over the square root of 6. And that is, in decimals, 0.816, 0.408, 0.408. Okay, so that's a unit vector in the direction of that force. And so that means that the force is this unit vector times our force variable TA. So negative 0.816 TA, positive 0.408 TA, positive 0.408 TA. And if you take that cross product, you get 0, negative 0.816 TA, positive 0.816 TA. Any questions about that one? So then we're going to use the same procedure for the other cable. What's the row vector for the second cable, the one connected at D? Yeah, 2.500. The force vector, we're going to do that the same way. So this was for that TA. Now we're going to do the same thing for TB. So what are the coordinates of the point B? 0x, 1.5y, negative 2z. Okay, so 0, 1.5, negative 2. And then the coordinates of D are 2.500. So the vector that's in the right direction is B minus D. So that's negative 2.5, 1.5, negative 2. And go through the same steps to get the unit vector. And you get that the unit vector is negative 0.707, positive 0.424, and negative 0.566. So the force vector is that unit vector times TB. So negative 0.707 TB, positive 0.424 TB, and negative 0.566 TB. And the cross product is 0x, 1.42 TB, 1.06 TB. By the way, there's one other way you could think about getting that unit vector besides finding the coordinates. You could just think of, so to get a vector that goes like from C to A, for example, you could think of the origin being here and just figure out what the vector is that you need to get from here to there. You know? So you'd have to go in the negative x direction 2, positive y direction 1, positive z direction 1, and you get the same thing that way. Okay. So now we got this thing. I'm going to move it to the other page. Oh, where am I? Here we go. Okay. So,
Scroll back up for a second.
yeah, sure. Sure. Any questions yet? Okay, so now Newton's second law just comes from the force column. We're just going to add all those up, set them equal to 0. So Rx, Ry, Rz plus 0, negative 490.5, 0, plus negative 0.816 TA, positive 0.408 TA, positive 0.408 TA, plus negative 707 TB, positive 0.424 TB, negative 0.566 TB, is equal to the 0 vector. And now same thing with the moment equation. So the 0 vector plus the vector 0, 0, negative 613.13 plus 0, negative 0.816 TB, positive 0.816 TB. What? Oh, thank you. Plus the vector 0, 1.42 TB, 1.06 TB is equal to the 0 vector. Okay, so there's our 6 equations. I said when I drew the free body diagram that we only had 5 variables, so one of our equations has to go away or it's not going to work. And you can see that the x component of the moment equation just gives us 0 equals 0. So we're left with the 5 equations that we need to solve for 5 variables. Does anyone want me to go through the matrix, set up the matrix, or you want me to just give you the answers for this? You'd set up a 5x6 matrix where one column represents every variable, the last column represents the constants, every row represents one of the 5 equations. And what you would get out of this when you do reduced row echelon form, you would get an R vector that's equal to 527.5 to 10.2, negative 35.1, and then TA is equal to 429.6. And TB is 247.7. Any questions about any of that?
The variables and the constants go across the columns on the sheet.
Yeah.
So your matrix.
So the matrix, the layout of the matrix would be like this. You'd have 5 rows, and each one of those represents one of the equations. And then 6 columns, and they would represent like Rx, Ry, Rz, Ta, Tb, and then the constants. Just remember to, in each one of those equations, you have to isolate the constant on the right side of the equation for this to work. Any other questions?
Is the one you were saying the other day that if you put the variables in some calculators, they'll stay there?
Yeah. In 89s, you can do that, and in Inspires, I think you can do that. I think the other ones you can't. So yeah, if you so let's see. The only way, so if you're doing that with reduced row echelon form, the way that would work is, you know how, like the thing that's loading this is the weight of the sign pulling down. If you took away that weight of the sign, all of these forces would just be 0 because the thing could just hover there. You could have problems where instead of this being driven by the weight, by like some known value, you could say it's driven by a downward force F. That's like a parameter, you know? And you can think of that F as really being a number that's part of the problem, you know? But what you would like ideally is to come up with your answers for these forces as functions of F. Okay? And so the way you would do a problem like that in your calculator is you would treat F like it was a number, you know? When you wrote out those equations, you'd get F alone on the right side of the equation or with other numbers. And then if you punch that, like put that in just like you do with numbers, your calculator would give you an answer at the end in terms of that F. Yeah, that's right.
So then like that would be useful if you were trying to determine the material to use for the sign.
Yep.
Like you have a certain.
Exactly. Yeah, you could use that for design, all sorts of design questions, you know, like, yeah, how much extra force you could put on it or whatever, you know, and you can optimize it based on that function. Right, exactly. Any other questions? Well, let's stop there. So test on Tuesday. And then,
Is that gonna be the whole time?
yeah. But I'm going to try really hard to, I mean, I always try not to make it like a race against the clock, sort of. So I think you'll have plenty, you won't feel rushed or anything, but yeah, you can leave when you're done. And then I'll do 1 or 2 more examples like this, and then we'll go on to centroids. Yeah.
When you find your tension on A and tension on B,
Mhm.
are you going to find many components or just magnitude?
Okay, so it depends. Like in this case, I asked for the tensions, so all we wanted was those magnitudes. But if I had asked for the force vectors, then you would take, yeah, so you just plug it back into the way they're represented in Newton's second law. Okay.